Welcome back. This video is on the Laplacian, which is actually the last derivative-like operation that we're going to consider it's actually the last vector calculus operation that we're going to consider in our course, and then we'll be ready to start applying these things. So let us have a look. The Laplacian is kind of goofy because it has a definition for scalar fields and then a separate definition for vector fields. So first of all, let's consider scalar fields. Okay, and we'll say scalar field T. We've been working with T quite a bit, like temperature. So we write the Laplacian, the notation looks like this, del squared, although it's not really a squaring operation, not in the strict sense. And so we would write del squared t, and we would pronounce that, as I just said, del squared t, or we would say the Laplacian of t. And it's defined as the divergence of the gradient. The divergence of the gradient. So that would be del dot del t. Divergence of the gradient. And we already talked about both of these operations separately, right? We talked about how to take the we talked about how to take the gradient, or how to compute the gradient of a scalar field t, that's in the parentheses. And then we talked about how to take the divergence of a vector, right? Because this thing in parentheses is a vector. The gradient of a scalar field is a vector. So let me ask you this, and please pause the video and think about this. The Laplacian of a scalar field, so this operation, does this operation give us a scalar, or does it give us a vector? Think about it. It gives us a scalar because the last operation that we perform is a dot product. The dot product is a scalar. So this thing is calculated like this. We take the second derivative of t with respect to x plus the second derivative of t with respect to y plus the second derivative of t with respect to z, right? And that is our scalar. We're just adding things up. So we'll just note that, yeah, that gives me a scalar back. And this is in Cartesian coordinates right here, right? X, Y, and Z. We can do something similar in cylindrical coordinates. This would be 1 over rho d rho, so the partial of rho times the partial on t with respect to rho, plus 1 over rho squared. And it's rho squared now because we're taking two partials. D squared t d phi squared, and then unsurprisingly it's just what you would expect, right? Because the z doesn't change from Cartesian to cylindrical. So this is in cylindrical coordinates. Cylindrical. All right, and again, unsurprisingly, the Laplacian has a computation in spherical coordinates as well. So this would be 1 over r squared again because we're taking two partial derivatives. So this is dr of r squared dt dr plus 1 over r squared sine of theta d theta sine theta dt d theta plus 1 over r squared sine squared theta second derivative of t with respect to phi. So this is in spherical coordinates. All right. So that's the Laplacian for a scalar field. And we would say that a scalar field t is harmonic. It's harmonic in a region if the Laplacian is equal to 0. If that's the case, then the field is harmonic, and that's called Laplace's equation. We saw something similar for divergence, right? If the divergence of a vector field was equal to 0, we called it solenoidal, just to remind you. Okay. All right, so that was for scalar fields, and for vector fields, it's defined a little bit differently. So let me erase this. Vector fields now. So let's say we have a vector field A. So we would still write del squared A, but now A gets the arrow because it's a vector field. And it's defined like this. The gradient of the divergence of A minus the curl of the curl of A. All right, so I'm going to ask you this again here. Does this operation result in a scalar, or does it result in a vector? Think about that. The answer to that is that we get a vector out. So here in this term, our last operation is take the gradient of this thing. The gradient is a vector. Here we're doing two curls. The curl is a vector. So this thing gives a vector out. And separately, we talked about how to compute all of these things. The divergence, the gradient, the curl in cylindrical, Cartesian, and spherical coordinates, so you should have no problem there. So, should you memorize these things? No. At this point, you should know that my philosophy is don't memorize these. You should be writing them down, having a sheet of notes that you can refer to, or bookmarking them in your textbook. And it might seem at this point where, wow, I've written a lot of things down. But remember, we're covering the math first in this course. And in fact, we're done, actually. That's it. We cover the math first. So now you've got your formula sheet or whatever you're doing. And now it's time to apply it. So you could compare this to like a construction worker where you've got a toolbox. You've filled your toolboxes with hammer, with saw, drill. Okay, now you're ready to use these tools and build your house or whatever. So this is it. This is our conclusion of vector calculus. You've seen all of the vector operations that we need, even going back to projection and adding vectors and so forth. Now, yes, we are ready to get into electromagnetics. So I will see you then.